engineers of the Boeing Company and the National Aeronautics and Space Administration are making final preparations to launch one of a series of lunar orbiters. The satellite's primary mission is to photograph landing areas on the moon for America's astronauts. An Atlas Agena booster will launch the orbiter from Cape Kennedy. When orbital speed and altitude are achieved, the Atlas booster and nose shroud will separate, and the Agena will fire to place itself and the lunar orbiter into a 100-mile-high orbit around the Earth. They must travel to the exact point in space from which Agena can put the lunar orbiter on its path to the moon. When this point is reached, Agena fires again. Soon after burnout, Agena separates, and the 850-pound orbiter will be on its way. Now speeding through space at 25,000 miles per hour, the vehicle will extend its two-way Earth communication antennas. And solar panels will open to capture and convert the sun's energy into electrical power for orbiter's systems. Tiny attitude control jets located on the corners of the heat shield will be fired to position the vehicle to aim its solar panels toward the sun, and aim its tracker for a fix on its navigational star, Canopus. After 15 hours of flight toward the moon, Lunar Orbiter will fire its velocity control rocket to make a mid-course correction. Later in the journey, as the orbiter gets closer to the moon, the velocity control rocket will be fired again to slow the spacecraft. This will serve to trap the spacecraft in an off-center orbit around the moon, where it will circle from 4 to 6 days. By tracking this orbit, scientists on Earth will obtain their first precise information about the effects of the moon's gravitational field on the spacecraft. With this knowledge, they will be able to lower the vehicle's orbit to a close 28 miles for photography of the moon's surface. Control of the spacecraft is accomplished through instructions stored in an onboard computer. Mission control personnel can radio new instructions for storage or can bypass the computer to control the orbiter directly. Operating on these instructions, the lunar orbiter will turn itself to aim its two camera lenses downward during picture-taking orbits. Then, as it soars over the desired areas, it will take a series of pictures. One lens will cover an area of 25 square miles and record objects as small as a card table. The other will make overlapping photographs of 440 square mile sections. During its mission, the lunar orbiter will take 160 pairs of pictures while filming 12,000 square miles, an area as large as the combined area of Massachusetts and Connecticut. While photography is in progress, the camera will begin to automatically develop and store the exposed film. Following each series of exposures, the orbiter will again aim its solar panels at the sun. When picture transmission takes place, the stored images will be sent in the form of an electronic signal produced by a light scanning the stored negatives. At Goldstone, near an abandoned gold mine in California's Mojave Desert, this 85-foot diameter antenna is the communication link with the lunar orbiter. It's similar to two other antennas in Australia and Spain, surrounding hills protected from random radio signals. The antenna control team tracks the orbiter with signals the orbiter sends back to Earth. The team also directs the flow of signals from the antenna to the orbiter. This equipment generates signals to the spacecraft. The orbiter's computer responds to the signals and controls the orbiter accordingly. These men are the last human link between Earth and the spacecraft. Incoming photographic information from the orbiter is fed into this equipment, where electronic wizardry converts the electronic signal to a pinpoint of light of varying intensity. The tiny beam sweeps back and forth, exposing a moving strip of 35mm film. When processed, the resulting negative shows what the orbiter's camera saw. At the receiving station, technicians will process and study samples of the exposed negative to ensure that signals are coming back properly and that the orbiter's camera is correctly set. Most of the 18 miles of film will be sent to a reassembly facility where the strips will be developed and arranged into large negatives. Prints of these negatives will form the basis for lunar maps. Although direct communication with the Lunar Orbiter is via Goldstone, or Australia, or Spain, the mission is directed from the Spaceflight Operations Facility in Pasadena. Sitting side by side, NASA and Boeing engineers evaluate and act upon information received from the antennas. The information comes to the Pasadena Computer Center and is translated into a form understandable to engineers. They use it to determine the lunar orbiter's velocity, attitude, temperature, power situation, and some 50 other conditions. This automatic drawing machine charts the data. Other engineers keep track of the orbiter's location and direction. They plot course changes and calculate when and how the spacecraft should be maneuvered. This control room is the nerve center of the entire mission. The operations director and his assistant are in voice contact with key personnel at those installations throughout the world which gather and record flight information. Engineers here at Pasadena interpret the information, and the operations directors use the results to make final flight decisions. When its photographic mission has been completed in about a month, the Lunar Orbiter will continue to circle the moon, providing information about micrometeoroids and radiation in the moon's vicinity. This data, along with the photographs, is vital to landing men on the moon.